A circuit with two hots, one neutral, and one ground running to a subpanel that supplies two or more branch circuits is a feeder. This is because it carries more than 120 amps, specifically 260 amp hots, and it supplies multiple branch circuits, meaning two or more. The grounding conductor size should follow the same sizing rules as the current carrying conductors, which are the hots and the neutral. The breaker size in a feeder circuit should be sized according to the ampacity of the smallest conductor in the feeder. Assuming the grounding conductor is the same size as the neutral and hots, it would be the determining factor. According to the National Electrical Code, Article 210.19 states that feeders shall be protected against overcurrent by either a circuit breaker or a fuse rated at not more than the ampacity of the conductor. Article 250.122 of the NEC states that the grounding electrode conductor shall not be smaller than the required grounding electrode conductor for the service or feeder. Based on these NEC requirements, the circuit should be treated as a feeder, and the breaker size should be sized according to the ampacity of the smallest conductor in the feeder, likely the grounding conductor. To further clarify feeder requirements, let's delve into more specific aspects of feeder design and installation. Firstly, feeder conductors must have sufficient ampacity to carry the calculated load, as per NEC 215.2. This calculation includes both continuous and non-continuous loads, ensuring the feeder can handle the expected current draw without overheating. Secondly, overcurrent protection for feeders is crucial. NEC 240.4 outlines the requirements for protecting conductors against overcurrent. The overcurrent device, such as a circuit breaker or fuse, must be sized to protect the feeder conductors based on their ampacity. This protection prevents damage to the conductors and reduces the risk of fire. Thirdly, grounding and bonding are essential for safety. Feeders must have an equipment grounding conductor EGC run with them to provide a low impedance path for fault current to return to the source. This ensures that overcurrent devices trip quickly in the event of a ground fault, minimizing the risk of electrical shock. NEC 250 provides detailed requirements for grounding and bonding of feeders. Furthermore, voltage drop is a consideration in feeder design. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. NEC 215.2 AFRI recommends limiting voltage drop on feeders to 3% to the furthest outlet for power, heating, and lighting loads, or a combined maximum voltage drop of 5% for both feeders and branch circuits. In addition to these general requirements, there are specific rules for different types of feeders. For example, TAP rules allow for reduced size feeder conductors under certain conditions, as outlined in NEC 240.21. These rules specify the maximum length of the TAP conductor and the required overcurrent protection. When installing feeders in specific environments, such as wet or corrosive locations, additional precautions must be taken. Conductors and equipment must be rated for the environment, and appropriate measures must be taken to prevent corrosion and moisture damage. NEC 300 provides general requirements for wiring methods, including those used for feeders. The size of the conduit or raceway used to enclose feeder conductors must be sufficient to accommodate the conductors and allow for proper heat dissipation. NEC Chapter 9 contains tables that specify the maximum number of conductors allowed in different sizes of conduit. Finally, proper labeling and identification of feeders are essential for safety and maintenance. Feeders should be clearly labeled at the source and at the point of termination to indicate the purpose and the circuits they serve. This helps prevent confusion and ensures that electrical work can be performed safely. In summary, understanding the requirements for feeder design and installation is crucial for ensuring a safe and reliable electrical system. By following the NEC guidelines and considering factors such as ampacity, overcurrent protection, grounding, voltage drop, and environmental conditions, electrical professionals can create feeder systems that meet the needs of the installation and protect people and property from electrical hazards. Let us now consider some practical examples to solidify your understanding. Imagine a scenario where you are installing a feeder to supply a detached garage from the main house. The garage will have lighting, receptacles, and a small electric heater. To determine the correct feeder size, you would first calculate the total load in the garage, including the lighting, receptacles, and heater. Then, you would select conductors with an ampacity sufficient to carry the calculated load, taking into account any dirtying factors for ambient temperature or conduit fill. You would also select an appropriately sized overcurrent device to protect the feeder conductors. In another scenario, consider a commercial building with multiple tenants. Each tenant space is supplied by a separate feeder from a main distribution panel. In this case, each feeder must be sized to accommodate the loads within the tenant space, and overcurrent protection must be provided to protect the feeder conductors. Additionally, the feeders must be properly labeled to indicate which tenant space they serve. Furthermore, let's explore some common mistakes to avoid when working with feeders. One common mistake is undersizing the feeder conductors. This can lead to overheating, voltage drop, and even fire. It is crucial to carefully calculate the load and select conductors with sufficient ampacity. Another mistake is improper grounding and bonding. This can create a shock hazard and prevent overcurrent devices from tripping properly in the event of a ground fault. Make sure to follow NEC 250 carefully when grounding and bonding feeders. Another potential pitfall is neglecting voltage drop. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. Use appropriately sized conductors and keep feeder runs as short as possible to minimize voltage drop. Additionally, failing to protect feeders from physical damage is a common error. Feeders should be installed in conduit or other approved raceways to protect them from damage. In wet or corrosive locations, use conductors and equipment that are rated for the environment. Moreover, it is crucial to follow all applicable electrical codes and standards when working with feeders. The NEC provides detailed requirements for feeder design, installation, and protection. Failure to comply with these requirements can result in serious consequences. When in doubt, consult with a qualified electrical inspector or engineer to ensure that your feeder installation is safe and code compliant. Remember, electrical work can be dangerous, so it is essential to take all necessary precautions. Wear appropriate personal protective equipment such as safety glasses and gloves, and always energize circuits before working on them. If you are not comfortable working with electricity, hire a qualified electrician to do the job. This ensures that the work is done safely and correctly. In conclusion, understanding the principles of feeder design and installation is essential for electrical professionals. By following the NEC guidelines and avoiding common mistakes, you can create safe, reliable, and efficient electrical systems. Let's address the implications of using undersized conductors for feeders. Undersized conductors can lead to several problems, including overheating, voltage drop, and fire hazards. When conductors are undersized, they are forced to carry more current than they are designed for. This causes the conductors to heat up, which can damage the insulation and potentially lead to a fire. Overheating can also damage the connected equipment and reduce its lifespan. Voltage drop occurs when the voltage at the end of a feeder is lower than the voltage at the source. This can cause equipment to malfunction or operate inefficiently. Excessive voltage drop can also lead to reduced lighting output and increased energy consumption. To prevent these problems, it is crucial to carefully calculate the load and select conductors with sufficient ampacity. Refer to NEC Table 310.16 for the ampacity of different conductor sizes and types. Take into account any dirtying factors for ambient temperature or conduit fill. Remember, it is always better to err on the side of caution and use conductors that are slightly larger than required. This will provide a margin of safety and ensure that the feeder can handle the expected load without any problems. Let's also examine the importance of proper overcurrent protection for feeders. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overloads and short circuits. When an overcurrent occurs, the overcurrent device trips, interrupting the flow of current and preventing damage to the conductors and equipment. It is crucial to select the correct size overcurrent device for the feeder conductors. The overcurrent device must be sized to protect the conductors based on their ampacity. Refer to NEC 240.4 for the requirements for overcurrent protection of conductors. If the overcurrent device is too small, it will trip unnecessarily, causing interruptions in service. If the overcurrent device is too large, it will not protect the conductors from overloads and short circuits. It is also important to ensure that the overcurrent device is properly installed and maintained. Overcurrent devices should be inspected regularly to ensure that they are in good working condition. Any damaged or defective overcurrent devices should be replaced immediately. Furthermore, let's consider the role of grounding and bonding in feeder systems. Grounding and bonding are essential for safety and are required by NEC 250. Grounding provides a low impedance path for fault current to return to the source. This ensures that overcurrent devices trip quickly in the event of a ground fault, minimizing the risk of electrical shock. Bonding connects all metal parts of the electrical system together to create a common ground potential. This prevents voltage differences between metal parts, which can cause electrical shock. When grounding feeders, it is crucial to use the correct size grounding electrode conductor. The size of the grounding electrode conductor is determined by the size of the feeder conductors. Refer to NEC Table 250.66 for the required size of the grounding electrode conductor. It is also important to ensure that the grounding electrode conductor is properly connected to a grounding electrode, such as a ground rod or a metal water pipe. When bonding feeders, it is crucial to bond all metal parts of the electrical system together, including conduit, equipment enclosures, and metal raceways. Bonding jumpers should be used to connect these metal parts together. Ensure that all bonding connections are tight and secure. Finally, let's discuss the importance of proper labeling and documentation for feeder systems. Proper labeling and documentation are essential for safety and maintenance. Feeders should be clearly labeled at the source and at the point of termination to indicate their purpose and the circuits they serve. This helps prevent confusion and ensures that electrical work can be performed safely. Documentation should include a detailed wiring diagram of the feeder system, including the size and type of conductors, the location of overcurrent devices, and the grounding and bonding connections. This documentation should be kept in a safe place and made available to qualified personnel. In summary, feeder systems are an essential part of any electrical installation. By understanding the principles of feeder design and installation, and by following the NEC guidelines, you can create safe, reliable, and efficient electrical systems. Always remember to prioritize safety and to consult with a qualified electrical professional when in doubt. With this comprehensive understanding, you are now better equipped to tackle electrical projects involving feeders with confidence and competence. Remember that continuous learning and staying updated with the latest code changes are crucial for success in the electrical field. Always prioritize safety and seek guidance from experienced professionals when facing complex situations.